We have defined different modes of convergence for a stochastic sequence or a random sequence, and in this video we want to learn a little bit more about the relationship between these modes of convergence. So particularly in this video we want to talk about a big theorem which is about this figure. So convergence everywhere, so we said that x of n converges to x everywhere, and we said that this is deterministic and these if this convergence is satisfied, it doesn't depend on probability distribution. All other modes of convergence they depend on the probability measure. Therefore, if you change the probability measure, they may become invalid. So therefore, this mode of convergence is the strongest one. And we will show that, for instance, convergence in distribution or law is weakest among the one that we defined. We will show that if you have convergence everywhere, you have convergence in mean square or L2 and so on, and we'll show that convergence in L2 is stronger than convergence L1, convergence in L3 is stronger than L2, and convergence in probability is weaker than L1. If you have convergence in probability, you can imply convergence in distribution and so on. So we see that there is this relationship is valid, but if you have this convergence, you cannot guarantee the upper level and so on. So this is why we call them the stronger one. Similarly, from convergence everywhere you can prove convergence almost everywhere. From convergence almost everywhere you can prove convergence in probability, but not the other way around. So you cannot go up, and here you cannot go up. Okay, so if you convert, for instance, if you prove convergence in L2 or mean square, all these convergences below that are automatically proven. So this theorem is something that we will quickly prove in this video. So justification and proof will quickly, some of these branches are easy to prove, so we just check mark, and some of them they need a little bit of tweak to get it proved. The proof is very easy, so you can follow it and then you can use it. We don't expect you to prove it in your exams, but we want you to remember this block diagram and then be able to use this one. So one of these branches can be easily proven using this inequality because, and this is easy, for a random variable xn minus x, you can always prove that this because this is a non-negative random variable, and then this is a Markov inequality, and then you can easily prove that because always mean of this guy divided by epsilon is smaller than this guy to the power of 2. So considering this inequality which is easy for you to prove, you can take the limit of all sides for all epsilon, and then let's say if this goes to 0, which means that if you have x of n converges to x in, let's say, L2, because this is non-negative, this one shall be 0 and this one shall be 0. So this simply proves this branch, okay? Because you can easily extend this theorem. You can easily show that this one is also smaller than mean of x of n minus x of n, let's say, to the power of 3, and third root of these divided by epsilon. So if you have convergence in L3, you have convergence L2 and also convergence L1. But this convergence doesn't force this one to become 0. So one branch is quickly proven. So remember that I have proven this branch, but not this last one. So the last one needs to be proven, this side needs to be proven, and so on. So the mean square convergence is stronger than L1, and L1 is stronger than the last one. So this is obvious. And L1 convergence is stronger than convergence in probability. Because if this becomes 0, or if this becomes 0, this shall be 0, and you get this one. So what we now need to do is to prove the other branch, which was in parallel. So so far we have proven this side, and now we want to prove this side. So we want to assume that you have convergence in almost everywhere, and we want to prove this one. And this is also very easy. So we assume that x of n converges to x, and it is easy to prove using a little bit of math trick that these should be converging to 0 using just the definition. And then you define this function, and then you say this function is continuous, and therefore this function, when you replace this x by xn minus x, also should converge to 0, and then you get this one, and then therefore the proof will become complete. So using this equation, and then because of this function, which is equal to this one, you can quickly do that. So so you can quickly prove that if you have this function, it is equal to put limit of probability of this one being greater than delta. For all epsilon, there exists some delta because of continuity of this function. So the other side is also proven, which is this part is also proven. So what you need to do is prove this one, and then the theorem is complete. So we shall show that the convergence in probability implies the convergence in distribution by virtue of the following arguments. This is very, very easy. So if you have any continuous bounded function means that for any 2 points, 2 values x and y, provided that the distance between g of x and g of y is bigger than delta, then x and y are far apart. So for all delta, there exists epsilon. So applying this one, replacing this one by x, replacing this one by x of n. So we substitute this one by x of n, and then so I replace this one by x of n, I replace this one by x of n, x, and then I calculate probability of this event. So because this event yields this event, so therefore probability of this one is smaller than this one. So this is obvious. So and this is true for any continuous bounded function, provided that for all delta you find epsilon which satisfy this equation. So this is so for all delta there exists epsilon which satisfy this probability, and obviously if n goes to infinity, because if you assume that this becomes 0, this shall be also 0. So for all delta, there exists epsilon, and this epsilon makes this one 0, so therefore this one is 0. So for all functions g, you have this guy 0. So this means that for all continuous bounded functions, if you have x of n converges to x in probability, any continuous unbounded function of x of n also converges into g of x. So in other words, all that, and this will simplify our function. So this implies this one, and then from here you can imply this, and the theorem is complete.